Hi, in this talk I'll give a brief overview of our method DAWN-FM, which is data-aware and noise-informed flow matching designed specifically for solving inverse problems under noisy and incomplete measurements. This is a joint work with Eldad Haber and was recently published in the journal Foundations of Data Science. Let us start by briefly describing what inverse problems are. Many problems in science and engineering often require us to infer quantities that we cannot observe directly. So instead of measuring a clean signal that we want, we only observe indirect and often noisy measurements produced by a physical system. The goal of solving an inverse problem then becomes recovering the underlying clean signal from these noisy measurements. We can look at some examples here. In each row, the image on the left represents the clean signal that we would like to recover. However, in practice, we do not observe this image directly. Instead, the measurements often undergo different physical or computational transformations. For example, images may be blurred due to optical limitations, corrupted by noise from sensors, partially missing as an image in painting, or reduced in resolution during acquisition. In medical imaging and tomography, we often observe projections such as the radon transform shown on the right rather than the image itself. Our goal then is to recover the original image from these degraded or indirect observations. In the previous slide, we saw several examples where measurements are degraded versions of an underlying image. Mathematically, all of these situations can be described using a common framework called a forward model. We model the measurement process using this equation. Here, A represents the forward operator, which models the physical measurement process. Depending on the application, this could represent blurring, downsampling, missing pixels, or projection operators such as the radon transform used in tomography. The variable x is the clean signal or the true image that we would want to recover, but this quantity is never observed directly. The term epsilon represents the measurement noise, which accounts for sensor imperfections and uncertainty in real-world data acquisition. And finally, B is the measured data, which is the only information available to us. The inverse problem is therefore the task of recovering x given only b, while the measurement process and noise have already destroyed part of the information. This loss of information is exactly what makes inverse problems fundamentally difficult and often non-unique and ill-posed. Now that we have defined the forward model mathematically, the natural question is how modern machine learning methods attempt to solve these inverse problems. One major class of approaches uses generative models as priors, particularly diffusion and score-based models. The idea here is to first learn the distribution of clean images using a large dataset and then use this pre-trained model as a regularizer when solving the inverse problem. During reconstruction, the algorithm searches for solutions that both match the measurement and lie on the learned data manifold. These methods have shown impressive visual quality and have become very popular in recent years. A second class of methods rely on encoder-decoder architectures. Instead of sampling from a generative model, these networks learn a mapping from measurement to the reconstructed images directly. Once trained, inference becomes extremely fast because reconstruction requires only a single forward pass through the network. However, these models typically learn an average solution and may struggle when the inverse problem admits multiple plausible reconstructions. A third direction integrates the physics directly into neural networks. Here, the forward operator is embedded inside the architecture or loss function so that the reconstruction remains consistent with the measured data. Some examples include methods that incorporate adjoint operators or iterative refinement inspired by classical inverse theory. While these approaches present significant progress, they also share several important limitations. Firstly, pre-trained generative priors are typically learned independently of the inverse problem itself. This means they may push solutions toward the average data distribution rather than towards solutions which are consistent with the specific measurements. Second, performance often deteriorates when noise levels vary or become very large, since the models are not explicitly aware of measurement noise. And finally, uncertainty estimation is often indirect or computationally expensive, even though inverse problems are inherently non-unique. Because of these challenges, it motivates us to propose a framework based on flow matching that learns the solution distribution directly conditioned on both the data and its noise level. To address the limitation of existing methods of solving inverse problems, we now turn to generative modeling framework known as flow matching. The main idea behind flow matching is surprisingly simple. Instead of directly generating complex data, we start from a very simple distribution, typically a Gaussian noise, and then learn how to continuously transform samples so that they gradually become realistic samples. Let's now look more closely at how flow matching works. The key idea is to define a smooth interpolation between two distributions. Here x0 is sampled from a simple Gaussian distribution and x1 is a clean sample from our dataset. The variable t lies in the interval 0 and 1 and controls how far along we are between noise levels and data. So when t equals 0, we are purely at Gaussian noise, and when t equals 1, we arrive at the true clean generated data point. For values in between, we obtain intermediate states that smoothly connect the 2 points. The learning objective is to estimate a velocity field denoted by s theta, which is a function of xt and t, where theta are typically learnable parameters of a neural network. This function tells us how a sample at position xt move at time t in order to reach the clean data distribution. So instead of directly learning to generate images, we learn the dynamics, that is the direction and speed at which samples evolve over time. After learning the velocity estimator, image generation becomes straightforward. We solve an initial value problem. We start from a random Gaussian noise at t equals 0 and then integrate this differential equation forward in time. As we evolve the system, the sample gradually transforms from noise into a realistic data point. In other words, flow matching learns a continuous transformation that reshapes a simple distribution into the target distribution as shown in the figure on the right. Standard flow matching learns the unconditional data distribution. However, when solving inverse problems, we are not sampling from the clean data distribution directly. Instead, we need to sample the posterior distribution of solutions given the measurement b. This means we must condition the generative process on our observed data. This brings us to our contribution DAWN-FM, where we propose a modified learnable velocity estimator which depends on the measured data and the measurement noise. This is achieved by conditioning the velocity estimator neural network on the measured data and the noise level. A transformation f of the measured data b is provided as embedding to the velocity estimator as the data condition. Additionally, a scalar embedding for the noise level sigma is incorporated into the network, allowing adaptation across different noise regimes. In many inverse problems, noise level significantly affects reconstruction quality. By explicitly providing sigma to the network, DAWN-FM learns how strongly to trust the measurement versus the prior. This improved velocity estimator allows the learned dynamics to adapt based on both data and uncertainty. To incorporate measurement information, we use the adjoint operator, which is A transpose. This maps the data back into the image domain and provides a physically meaningful and physics-aware representation for conditioning. The exact architectural details for the velocity estimator network can be found in our paper mentioned in the footnote of this slide. The figure on the right illustrates the key difference between standard flow matching and DAWN-FM. In standard flow matching, the learned dynamics transport Gaussian noise towards the general data distribution. This means that the trajectory can end up at any plausible image in the target distribution. However, in inverse problems, we are not interested in just any realistic image. We want the specific image that is consistent with the measured data. By conditioning the velocity field on the measurement embedding FB and the noise level sigma, the flow is no longer unconstrained. Instead of drifting towards an arbitrary point in the clean data manifold, the trajectory is steered towards the subset of images that explain the observed measurements. We train DAWN-FM using two complementary objectives. First, we retain the standard flow matching velocity loss, which encourages the network to learn the correct transport dynamics between noise and data. This ensures that the learned velocity vector remains consistent with the underlying probability flow formulation. Second, we introduce a data consistency loss that penalizes discrepancies between the forward projection of the predicted sample and the actual measured data. In other words, the generated solution must not only look realistic, but must also produce the measurements when passed through the forward operator. By combining these two losses, we simultaneously learn physically meaningful dynamics and enforce agreement with the observed data. This allows DAWN-FM to model the posterior distribution rather than just the unconditional data distribution. After training, the inference is straightforward and fully generative. First, we initialize a sample from a Gaussian distribution, just as in standard flow matching. Then we integrate the learned conditioned velocity field to forward in time by solving this ODE. Because the velocity depends on the measurement embedding as well as the noise level, the trajectory is guided towards solutions that are consistent with the observed data. By repeating this process with different random initializations, we obtain multiple posterior samples. On the right, we show an example from the deblurring task. Although each generated image is slightly different, they all correspond to the same measured data. This variability reflects the inherent uncertainty of the inverse problem rather than model instability. One of the key advantages of DON-FM is that it naturally enables uncertainty estimation through posterior sampling. After conditioning the model on blurred measurements, we generate multiple samples from the learned posterior distribution. Each of these samples is a plausible reconstruction consistent with the measured data. The posterior mean, obtained by averaging across all generated samples, provides a stable and high quality reconstruction as shown in the center image. More importantly, we compute the posterior variance across samples on a pixel-wise basis. This produces the uncertainty map shown on the right. We observe that uncertainty is higher along edges and regions where the measurement process removes more information. This in turn reflects the intrinsic ambiguity of inverse problem rather than model instability. In this way, DON-FM does not just output a single reconstruction, it characterizes the full distribution of plausible solutions. This probabilistic perspective allows us to quantify confidence in the reconstruction, which is crucial in several scientific and imaging applications. Now let us discuss our experiments for the deblurring task. The quantitative results for the deblurring task across MNIST, STL10 and CFA10 datasets are presented in the table here. We compare DON-FM against diffusion-based priors and inverse unit ODE. We also compare to our DAW-FM variant, which incorporates only the data but no noise embedding in the velocity estimator network. Performance is evaluated using metrics such as the mean squared error and data misfit, where lower is better, and SSIM and PSNR, where higher is better. Across all datasets, DON-FM consistently outperforms baseline approaches in both error-based and perceptual metrics. Overall, these results demonstrate that conditioning the flow on both data and noise leads to consistently improved reconstruction quality across different datasets and noise regimes. This figure shows how performance evolves as we increase the noise level in the measurements. The solid line shows the results of DON-FM and the dashed line shows the results of DAW-FM, which is our variant with no noise embedding. Across all datasets and evaluation metrics, we observe a consistent trend. DON-FM degrades much more slowly as noise increases. In terms of reconstruction error and misfit, the gap between DON-FM and baseline method widens at higher noise levels, indicating improved robustness to noise. Similarly, for perceptual metrics such as SSIM and PSNR, DON-FM maintains higher values even under severe degradation. This behavior highlights a key advantage of our approach. Explicitly conditioning on the noise level allows the learned dynamics to adapt to different uncertainty regimes. As noise increases, the model automatically adjusts how strongly it trusts the data versus the learned prior, leading to a more stable reconstruction. In short, DON-FM is not only accurate at low noise levels, but it remains reliable and robust as the inverse problem becomes increasingly ill-posed at higher noise levels. We also evaluate DON-FM on 2D tomography tasks and compare it against classical filtered back projection as well as our earlier DAW-FM variant. Across two datasets, organ A MNIST and organ C MNIST, DON-FM consistently achieves lower reconstruction error and higher SSIM and PSNR. Moreover, for the deblurring task, DON-FM consistently recovers clearer structures and more faithful details, particularly in challenging high noise scenarios. Here we consider 5% and 7% added noise in the blurred data. A similar pattern holds in the 2D tomography task, where DON-FM delivers cleaner reconstructions and better structural preservation under noisy measurements as compared to baselines. So in summary, we address the challenge of solving ill-posed inverse problems under noisy measurements. We propose DON-FM, a data-aware and noise-informed flow matching framework that conditions the velocity field on both the measurements and the noise level. By incorporating a physics-aware embedding through the adjoint operator, the learned dynamics are guided towards data-consistent solutions rather than arbitrary points in the image distribution. This allows us to not only improve reconstruction quality across tasks such as deblurring and tomography, but it also helps us obtain principled uncertainty estimates via posterior sampling. Overall, DON-FM provides a unified probabilistic framework that bridges generative modeling and physics-based inverse problem solving. Thank you for your attention. The open source implementation, early access journal version, and the archive preprints are available through the QR code shown here. Feel free to reach out if you have any questions about our work. Thank you.